Intermittent fasting acts as a potent biological trigger for neuroprotection. Depriving the body of calories forces neural networks into a state of high-efficiency preservation, activating mechanisms that repair and generate new brain cells. In human populations, the most widespread execution of this metabolic state occurs during Ramadan. This protocol requires strict dawn-to-dusk restriction of both caloric intake and fluids. When researchers track cognitive performance clinically during this month-long period, the data yields conflicting, often paradoxical results. Some clinical studies record significant enhancements in memory and executive function by the end of the fasting month. Parallel studies document sharp declines in simple reaction times and vigilance. Cognitive output fluctuates according to a complex neurometabolic matrix, shifting based on timing and biological status. Reconciling these results involves examining cellular biology, metabolic health, circadian timing, and hydration levels. Predicting a person's cognitive performance requires separating the theoretical cellular benefits of fasting from the acute behavioral stressors imposed by the protocol's parameters. At the molecular level, standard intermittent fasting initiates cellular mechanics designed to protect the brain. The primary mechanism is autophagy, a cellular degradation process where cells break down and clear out their own damaged components, reducing oxidative stress. This process upregulates hippocampal brain-derived neurotrophic factor, or BDNF, a protein that promotes the survival of nerve cells and the growth of new synapses. As misfolded proteins are cleared, neuronal membranes stabilize and BDNF levels climb. These pathways explain the positive outcomes seen in animal models and the measurable clinical benefits for patients managing neurodegenerative diseases like Alzheimer's. However, the human behavioral reality of Ramadan differs from standard fasting. The protocol introduces strict fluid restriction and enforces circadian disruption via nighttime meals, known as suhoor, the pre-dawn meal consumed before starting the daily fast. This graph maps diurnal variation in cognitive performance, measuring output from morning to evening during the fasting state. The morning data proves that performance on reaction times and forward-type digit span tests, which measure working memory capacity, remains stable or occasionally improves during the AM hours. But as the timeline crosses into the PM hours, the plotted data reveals sharp degradations in vigilance, choice reaction times, and mental rotation tasks. Physical and mental fatigue accumulate over the course of the workday without caloric replenishment, driving this afternoon dip. Disrupted sleep further impacts performance. Waking for suhoor interrupts standard REM and deep sleep cycles, directly lowering afternoon alertness. Hypohydration also plays a role. Clinical data confirms that dehydration critically slows reaction speeds when compared to euhydrated or normally hydrated states. While the brain's architecture is biochemically primed for enhancement, the acute environmental stressors of the Ramadan protocol transiently override these benefits in the afternoon hours. Baseline metabolic health acts as the physiological gatekeeper for these effects. Pre-existing conditions dictate whether fasting enhances or accelerates cognitive decline. This scatter plot correlates metabolic markers against cognitive assessment scores, specifically the BICAMS, the Brief International Cognitive Assessment for MS, and the CASI, the Cognitive Abilities Screening Instrument. High fasting blood glucose, or FBG, and high insulin levels actively neutralize fasting gains. FBG is a test measuring sugar levels in the blood after a period of not eating. Elevated levels correlate with the lowest cognitive scores. Furthermore, high visit-to-visit variability in HbA1c is associated with a modest decline in global cognitive performance, particularly in adults at high risk for type 2 diabetes. HbA1c is a marker reflecting average blood sugar levels over several months. Combining low serum uric acid with high fasting plasma glucose exacerbates cognitive impairment, an effect specifically prominent among women. Both markers indicate metabolic stability, and their imbalance accelerates neurodegeneration. Poor metabolic markers create oxidative distress during the periods the body is deprived of glucose, actively damaging neural pathways. For metabolically compromised populations, the physiological stress of fasting acts as a bottleneck that nullifies cellular benefits and worsens cognitive function. Specific interventions, known as active mitigators, can shift the cognitive data back toward enhancement. Fasting produces superior cognitive performance when paired with plant-rich diets and probiotic supplementation. These dietary factors directly influence the microbiotic gut-brain axis, the biochemical signaling network connecting the gastrointestinal tract with the central nervous system, effectively regulating neuroinflammation. Exercise data presents another mitigator. Engaging in short-term maximal exercise in the evening mitigates fasting-induced cognitive impairments and improves selective attention. This timeline graphs executive function and mood across the entire 4-week chronological adaptation period. During the middle of the month, cognitive anxiety and deficits in reaction times hit their highest point as the body struggles to adjust to the new metabolic schedule. By the final week, the data shows significant improvements in memory, concentration, and lowered mood disturbance scores, stabilizing above the pre-fasting baseline. The human brain requires this chronological adaptation period. By week 4, the brain successfully leverages cellular neuroprotective benefits to overcome the initial behavioral stressors. Clinical literature suggests that fasting's impact on the brain depends entirely on how specific physiological variables are managed. 3 primary factors determine cognitive output during the fast. First, cellular neuroprotection through BDNF and autophagy clears damaged proteins. Second, fatigue and dehydration transiently compromise behavioral outputs in the afternoon. Finally, baseline metabolic health and insulin sensitivity dictate whether the brain successfully adapts. By controlling metabolic baselines and mitigating sleep and hydration deficits, the cognitive architecture can leverage the physiological stress of fasting for long-term neurocognitive enhancement.